Okay, section 3.5, putting it all together. So we're going to analyze functions using derivatives and do a complete curve sketching question. And so the example I picked here is this quartic polynomial, degree 4. Okay, so if you remember advanced functions, we talked about this kind of polynomial, and you may remember a few things, right? So with a fourth degree polynomial, it's an even degree function, which tells us a few things. So for a fourth degree polynomial, you've got potentially up to 4 real roots, 3 turning points, and with the positive leading coefficients, we have the invisible positive 1 here. And an even degree function means the end behaviors are going to be in quadrant 1 and quadrant 2. So it's going to end in quadrant 1 and quadrant 2. So that tells us quite a bit. Now we're going to put in some calculus in here with the first derivatives and the second derivatives to help us determine the locations of maximums and minimums, as well as any potential points of inflection. Okay, so we're going to do that now. Starting with A, state the domain of the function f of x. So for any polynomial, we know polynomials are continuous functions. There are no restrictions in the domain. This is not a piecewise function with any restrictions. So we can state here that for part A, the domain is x is every real number, and I'm just using my curly brace brackets. My set notation here. All right. Part B, determine the x and y intercepts. So this question will serve as some good review of some of our advanced functions concepts, such as the factor theorem, as well as polynomial division. Okay, I want to factor this polynomial in order to get the x intercepts. Okay, so let's do that. So with our factor theorem, if you remember the factor theorem, if f of some value a equals 0, then x minus a is a factor. Okay, so I need to find that value of a, and your potential candidates are going to, well, for this polynomial, are going to come from the last constant term. And if you remember the last constant term, if I took the factors of that last constant term, I have potential candidates for the factor theorem. So I could have here plus or minus 1 as a factor, 2 as well, 3 times 6 is 18 as well, 9, 2 times 9, and then don't forget 1 times 18. So we have quite a few numbers to test here. So we're going to try 1. Okay, and so if I do f of 1, we will get, so x to the power of 4 is 1 to the power of 4, minus 5x cubed, so minus 5 times 1 cubed, and then we have plus 1 squared, or x squared, so plus 1 squared, and then we have 21x, so plus 21 times 1, and then we have the minus 18. Okay, so all is there and present and accounted for. Now if I kind of simplify this, we have 1 minus 5 plus 1 plus 21 minus 18. And it turns out when I add up all those numbers, we get 0. F of 1 equals 0. So, therefore, x minus 1, right, x minus a, x minus 1 is a factor. It's good we're reviewing this now because this is going to, again, come up in the final exam when we do advanced functions. You don't want to forget this stuff. Okay, so if we know one of the factors, we can use polynomial division to help us determine the rest of the factors. Okay, and just to go even further, I'm going to use synthetic division. It's a little bit faster, so we're going to use synthetic division to find other factors. Okay, So synthetic division, here we go. 1, so if x minus 1 is a factor, I'm going to put the 1 on the outside here. And I'm going to draw my chart, my L shape. And I'm going to put the coefficients of my function in the proper order from the highest degree to the lowest degree. Excuse me. Ooh. Okay, so the coefficient of x to the power 4 is 1. And then the minus 5x cubed, we have a minus 5. And then we have the 1x squared, so we have a 1. And then we have the 21x, so we have a positive 21. And then we have the minus 18 at the end. And if you recall synthetic division, it means you start with the 1, we bring it down, multiply it with the factor, or the divisor. 1 times 1 is 1, bring that up here, and then negative 5 plus 1. We add the columns, right? So you multiply, then add, multiply, then add. So 1 times negative 4, we multiply, we get negative 4. And then we add. 1 plus negative 4 is negative 3. Multiply, we get negative 3. 21 minus 3, so we add these two numbers together, we get 18. And then 18 times 1 is 18. Add this last column, negative 18 plus 18 is 0. And if you did everything right, yeah, remember the remainder, r must be 0, because we're factoring here. Okay, so we have another polynomial. It's a cubic this time, so x cubed minus 4x squared minus 3x plus 18. So remember the quotient, these are the coefficients of my quotient polynomial. Now this is not fully factored yet, so we're going to have to use factor theorem again. So use factor theorem again. Okay, and so let's try another number. We could try 2, right? F of 2. Okay, if I tried 2, is that another factor of f of x? I'm talking about the original f of x. So, right, so we do to the power 4 minus 5 times 2 cubed plus 2 squared plus 21 times 2 minus 18. Nah, that's not equal to 0, okay? If I tried f of negative 2, we get negative 2 to the power of 4, which is 16, minus 5 times negative 2 cubed. Double negatives makes positive. 8 times 5 is 40. Okay, and then the plus minus 2 squared, or negative 2 squared, which is 4, so plus 4. And then we have a plus 21 times negative 2, so it's minus 42. And then minus 18, and I believe that turns out to be 0. Okay, so we have another factor, right? So x plus 2, so therefore x plus 2 is a factor, okay? And then we can continue polynomial division again, right? So if I did polynomial division again, I'm going to write here negative 2 as my divisor. Write down the chart, the coefficients of the quotient that I found here, up here, x cubed minus 4x squared minus 3x plus 18. I'm going to write those coefficients in my synthetic division. So 1 minus 4 minus 3 and 18, okay? And then we carry out the division. Bring down the 1, multiply it by negative 2, write that in the next column. Add the column, negative 4 plus negative 2 is negative 6. Multiply negative 2 times negative 6 is 12. Add the column, you get 9. Negative 2 times 9 is negative 18. 18 plus negative 18 is 0. So again, the remainder equals 0 as expected. And we were hoping to get that. And if we didn't, we would have double checked to see if there's something wrong. Okay. And so here the quotient now is x squared minus 6x plus 9. So let's write out the factored form of f of x. Right? So we have f of x equals, from the factor theorem the first time, we have x minus 1 as a factor. In the factor theorem a second time, we have x plus 2 as a factor. And then from x squared minus 6x plus 9, that's factorable. That's x minus 3 squared. That's a perfect square factoring there. So there is our fully factored form. This is now fully factored. And from this form, I can obtain my intercepts, my x-intercepts. So where 0 equals x minus 1 times x plus 2 times x minus 3 squared, we have x equals 1, minus 2, and 3. And remember, in advanced functions, we said something about what happens when one of the factors is squared. Then this x-intercept, or this root, has a multiplicity of 2, which means at the root, what's happening if this is your x-intercept, right? Your root is not going to cross, it's going to turn around, okay? So keep that in mind. So those are the x-intercepts. We also have to find the y-intercept. And just remember the y-intercept, just plug in a 0. F of 0 is just that last constant at the very end because all the other terms have x in it. And so you're going to adding a bunch of 0 terms. And at the end, you have the minus 18. So there's your y-intercept at 0 and negative 18. So let's just write this out. X-intercepts are 1 and 0, negative 2 and 0, and 3 and 0, and my y-intercept is 0 and negative 18. Okay, so far, no calculus here. This was just advanced functions stuff. Part C is now where we introduce our calculus concepts here. So we're going to look at critical points. Critical points require us, part C, determine any critical points. So we will need our first derivative. So part C, reminding ourselves again, for the critical points, find f prime of x. Okay, so f prime of x equals 4x cubed. So again, power rule here, 4x to the power 4 becomes 4x cubed. Minus 5x cubed becomes minus 5 times 3, which is 15. Reduce the exponent of x, so it becomes x squared. And then the x squared term becomes 2x, so plus 2x. And then the 21x term becomes plus 21. And then the minus 18 is gone because minus 18 is just a constant. So here's my derivative. It's a cubic polynomial, 1 degree less than f of x. So let's now find the critical points. And remember, to do that, we have to set the derivative equal to 0. Okay, so 0 equals 4x cubed minus 15x squared plus 2x plus 21. How do we factor this? Well, we got to factor this, I should say. We're trying to find a 0, right? So we got to factor this, which means we got to use factor theorem again. We got to look at all the factors of 21, and we've got plus or minus 1, 3 and 7. 3 times 7 is 21, right? And then 21 itself. So fewer factors to test. We'll get there sooner. So let's start testing them. Factor theorem, f prime. We're not saying f now, we're saying f prime of 1. Okay, we're going to test that. So 4 times 1 cubed minus 15 times 1 squared plus 2 times 1 plus 21. So positive, bigger positive minus only a 15 times 1. Yeah, that's not going to be 0. Okay, not 0. Let's try negative 1. So f prime of negative 1 equals 4 times negative 1 cubed minus 15 times negative 1 squared plus 2 times negative 1 plus 21. Okay, and that's equal to 0. So there's our factor, right? So therefore, x plus 1 is a factor. And so let's apply synthetic division again. We're going to write here minus 1 as our divisor. Draw our L shape. Write down the coefficients 4, negative 15, 2, and 21. Carry out the synthetic division. Bring down the 4. Multiply with the divisor. 4 times negative 1 is negative 4. Add the next column. Negative 15 plus negative 4 is negative 19. Multiply again. We get positive 19. 2 plus 19 is positive 21. Multiply again, we get negative 21, and then 21 plus negative 21 is 0. Okay, and so the factored form of my derivative, f prime x, is going to be x plus 1 times my quotient, 4x squared minus 19x plus 21. Okay, and then we're going to factor this even further. X, this is factorable, right? This is quadratic, right? So we can have a 4x times x. And to make 21, we need 7 and 3, right? Like there's not many choices to choose from. And then so if I put the 7 here and the 3 here, 3 times 4 is 12. 12 plus 7x is 19x, so I got to make both of them negative. Okay, so 4x minus 7 and then x minus 3. And that gives me 3 critical points. We have a critical point at x equals negative 1. Oh, so yeah, I forgot to say, set the derivative equal to 0, right, to find your critical points. And so we have x equals negative 1 as a critical point. We have x equals 7 over 4 as a critical point. And we have x equals 3 as a critical point. Okay. Now, just for brevity here, I'm going to say here, critical points are at, and I will just give you the y values. So at f of negative 1, we have negative 32. At f of 7 over 4, we have something approximately equal to 4.39. And then at f of 3, we have 0. Okay. Now I'm going to use an interval chart here just to determine whether these critical points are maximums and minimums. Okay, so I'm going to take out a ruler. Let's draw a line. I'm going to need 4 intervals with 3 critical points. So let's do 4 intervals. So first interval, second interval, and then third interval. Extend that a little bit more. Okay. So here I'm going to find the sign of f prime x and the corresponding whether the graph is increasing or decreasing for f of x. Remember the derivative, the sign of the derivative tells us whether f of x is increasing or decreasing. So my first interval is going to be from negative infinity to negative 1. The second interval will be from negative 1 to 7 quarters. The next interval will be 7 quarters to 3, and then my last interval will be from 3 to infinity. Okay, and this is in interval notation. So now if you plot test points into your first derivative, right? So for my first interval, you could try negative 2. So when you look at the factors here, right, negative 2 plus 1 is a negative. 4 times negative 2 minus 7 is a negative, and negative 2 minus 3 is a negative. 3 negatives, when I multiply them, become negative. So the result is negative for the derivative. And so that means f of x is decreasing. Okay. For the interval from negative 1 to 7/4, you could pick 0, for example. And if I did 0, I get x plus 1 is positive. 4x minus 7 is negative. X minus 3 is negative. 2 negatives make a positive. So we get a positive derivative. And the graph of f of x is increasing. Okay, and no time do I really need the exact f prime value. Just give me the sign. So the sign of f prime. And similarly, if you do the last 2 intervals, you're going to get a negative for the third one here. And then for everything to the right of 3, you'll get a positive interval. And so we're going to have decreasing and then increasing. So what are my critical points? Based on the changes in the derivative, we have a minimum points, local minimum points at negative 1. So negative 1 and the corresponding y value is negative 32. And at 3. 3 and its corresponding y value is 0. Okay. And the maximum points are at 7/4, and we said the corresponding y value is about 4.39. Okay, so there you have it. Those are our local extremum, local max, local mins. Okay, so to continue finishing this question, we will also need to know how our graph curves. Intervals of concavity, second derivative. Let's calculate the second derivative. F double prime x. Okay. If I calculate the second derivative, we're looking at the derivative of the first derivative. So I'm going to go back to the, well, let's remind ourselves of the first derivative. Let's write that down. Maybe we'll take this, go to the next page. So maybe you run out of space in your page. So f prime x, let's remind ourselves, f prime x is 4x cubed minus 15x squared plus 2x plus 21. Okay. And then, so if I take the second derivative, f double prime x equals 12. 4 times 3 is 12, 12x squared. And then 15 times 2 is 30, so minus 30x, and then a plus 2. Okay. Is this factorable? B squared minus 4ac does not look like it. Well, you know what? Let's just use the quadratic formula. I don't think it is factorable. So let's use the quadratic formula. Use the quadratic formula to find the roots. Okay, so remember, we're trying to solve. We're gonna set f double prime x equal to 0, because that's the condition we need to help us find some potential critical points. So set f double prime x equal to 0 to find, sorry, not critical points, what did I say? Points of inflection, that's what I meant to say. To find points of inflection. Okay, points of inflection. Okay, quadratic formula. Do you remember what it is? X equals negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so if I plug in my values here, yeah, okay, let's plug in the values here. X equals negative b, so negative of negative 30, which is positive 30, plus or minus the square root of negative 30 squared, minus 4 times a, which we said was 12, times c, which is 2. Right? Just double check. So my screen is freezing. Oh, 2, okay. All over 2 times a, which is 12. Okay, so if you calculate out the x, you should get two answers, 2.43 and 0.07. Okay, so not nice numbers, but you can still work with them, right? The corresponding y values for 2.43 is 2.06, and the corresponding y value for x equals 0.7 is about negative 16.53. Okay. Now, are these points of inflection? They're not guaranteed until you actually carry out the work to determine if they are. So we're going to create another chart. And we're going to have 3 intervals. Okay, we're going to look at the sign of the second derivative, and the sign of the second derivative will tell us the concavity of the function. So we're going to look at the interval from negative infinity to 0.07. Let me draw that better. There we go. The interval from 0.07 to 2.43. And the interval from 2.43 to infinity. Okay. So let's take a test point from negative infinity to negative 0.07. Pick a negative 1. Plug it into the second derivative. All right, so negative 12 times negative 1 squared is a positive number. To be precise, it's going to be 12. Minus 30 times negative 1, so it's plus 30 more. Plus 2, that's a positive. All results in a positive. Okay, positive sign for the second derivative, which means the graph of f of x is concave up. Between 0.07 and 2.43, pick a 1. 12x squared is 1. 12. 1 times 12. Minus 30 plus 2. Oh, that's going to be a negative number. Okay, that's a negative number. And that means f of x is concave down in that interval. So we have a change in concavity. What does that mean? We have a point of inflection at 0.07. What about 2.43 and to the right? So you could pick a test value of 3. If I pick a test value of 3, f double prime of 3 is 12 times 3 squared, which is 9 times 12 minus 30 times 3, which is 90, and then plus 2. I believe that's slightly positive. 12 times 9 is over 100. Okay, so there we go. Plus concave up. And so we have another point of inflection. So it goes from concave down to concave up at 2.43. So we have a point of inflection. So these two are points of inflection. Okay. Do we have enough information to now graph this? I think we do. Okay, let's look at the graph. We can plot our x-intercepts first. Why don't we do that? Negative 2 is an x-intercept. We have 1 as an x-intercept. And we have 3 as an x-intercept. Okay, remember the end behaviors. We have to end somewhere here, and then we have to end somewhere here. Okay, this x to the power, the function is an x to the power 4, right? Quadrant 1 and quadrant 3. Which means when we cross the x-axis at negative 2, it's probably going to cross something like this. Crosses straight through from quadrant 3 into quadrant, quadrant 2 to quadrant 3. What did I say? Quadrant 1 and quadrant 2. End behaviors are quadrant 1, quadrant 2. I think I mentioned that in the beginning. Hope I didn't stumble over that in the beginning. But yeah, that's what I'm talking about. Okay. And then you're going to have to cross back through 1. So you're going to have to cross this way, right? Not the other way because you don't have any other x-intercepts in between. And we said the root at 3 had a multiplicity of 2. So we'll probably have to curve back like this. Something like that. All right. Turning points. So where are our turning points? We have a turning point at negative 1 and at, let's remind ourselves again, negative 1 we have a minimum, and at 3 we have a minimum. So, okay, so our x-intercept with a multiplicity of 2 is a turning point. All right. Okay, and we have negative 1 and negative 32. Okay, so there we go. Let's plot that negative 1 and negative 32. That's a minimum. So our graph might look like that. And the maximum point, the local maximum, we said was 7 over 4 and 4.39. Okay, so it's a number close to 2, between 1 and 2, but closer to 2. Okay, so we're going to say the y value 4.39, maybe somewhere around here. Okay. And then we have a point of inflections. The points of inflections are at, what do we say? 0.07 and 2.43. Okay. And my y-intercept. Don't forget the y-intercept is at minus 18. So somewhere around here. Point of inflection is at minus 16. Yeah. 0.07, and minus 16, so maybe somewhere around here. And the other point of inflection is 2.43, 2.06. Okay, so 2.43, halfway between 2 and 3 almost. And what was the y value again? 2.06. Oh, that's pretty low. Maybe somewhere around here. Okay, I might have to change that turning point. So, okay, so get some turning point like that. Let me fix that. That looked better. Okay. Okay. So I think we've got what we need, right? So we start at quadrant 2. Let's just draw an arrow like that. We cross that x-axis. We go all the way down to our minimum point here. Turn around. And remember, we're concave up at up until 0.07. So we're gonna have to show that a little bit. I don't like how I did that, so let's just fix that. Is that any better? Not quite sure. I think I gotta make this more. There we go. Not quite what I hope to have, but it's a sketch. All right. So remember, concave up for this portion of the graph. Then we have concave down from my first red point to my left to the second red point. So it's gonna be concave down. Gotta obey the other points here. So you have to cross the x-intercept. And we have another maximum, a local maximum. So it turns around until I reach the second red point. So here's my interval. It's concave down. And then the last interval is concave up. And there it is, concave up. So there is a reasonable approximation of this function, quartic function. Okay, with where are my turning points again? Turning point, turning point, turning point, 3 turning points. All right. That is an example of a curve sketching problem. And you have a few questions to try on your own. Have a look at page 192, numbers 4, 5, and 9 for some curve sketching practice. And that's it. That ends this video. See you in the next lesson.